Hello and welcome to How to Math with Dr. Ian Lundholm. In today's episode, Power Series. All right, so today's all about power series. We're going to introduce the terms of power series, look at some examples. We're going to talk about the radius of convergence because these power series don't converge everywhere. They only converge for certain values of x. And then we will talk about how power series are, definitely related to calculus and the fact that they can be differentiated and integrated. Power series really are just infinitely long polynomials, if you want to think about it that way. Here's a general form of a power series. And you might notice, right from the beginning that, for any certain value of x here, this series would look an awful lot like a geometric series because you end up taking, various powers of x along the way. Those just keep increasing as you go on. So we will definitely be making reference to geometric series a lot during this lesson. There's connections to be made there. One of the big differences now is, x is a variable, and we're allowed to put in, whatever real numbers we might want to in for x. And one of our major concerns in this chapter will be, for given values of x, will this series converge or diverge? I guess, yeah. And the other thing is that since these constants out in front of the powers of x, they could be different as, n goes on. That's another way that it's kind of different from just a strict geometric series, but there's that. Yeah. If all of the, C1 through Cn were maybe just the number one, then it would be a nice geometric series to some extent. If all of those coefficients were just one, it would be a geometric series. Okay. This top one is centered at 0, and more generally, you can center a power series around an x value, and we call that x value a. By setting it up like this, this kind of a format hopefully rings some bells in terms of, transformations on single variable functions. Like if we wanted to take the function, let's say x squared, and we wanted, and that's just a parabola, right? If we wanted to shift this parabola so that, it came over here and was centered at some point A, the way that we would do that is, right, x minus a squared. That's a horizontal shift. So that's what it means to be, centered about an x value a. Here we go. For any fixed x, the power series is definitely similar to geometric series a lot of times. Yes, I've already said that we want to determine all values of x where the power series converges. And yes, it's possible that we might converge or diverge depending on what the power series looks like. So we're going to keep looking into that. Here we've got 3 examples. In this first one, the top part is looking fairly geometric. We've got something, raised to the n power. I guess the bottom part kind of reminds me of the harmonic series too, that 1 over n thing. But, in this series, the top part is going to play more of a central role because it is in that kind of geometric setup where the n is in the power. So look out for the top part being more important there. Here we've got something that looks like an alternating series for part B. And then this one looks crazy because we've got a factorial out front as like our coefficients. And those things get huge. So let's take a look and think about what values of x these things will converge for. And in order to determine that, we're going to be using the ratio test. That's going to be the test that we use throughout this whole section. So ratio test, we're looking at the ratio between the n plus 1th term and the nth term. Here we go for our first series. Do notice that the absolute value signs in the ratio test are pretty important in this context. We're able to, have absolute value signs around the x minus 5 here in the end. And this part, as, n goes to infinity, this part will go to 1. Cool. So, by this ratio test, we definitely know that the power series will converge if the difference between the x value and 5 is less than 1. So, we know definitely... What? Come back. Sorry. We definitely know at this point that x in between 4 and 6 should work. But remember that by the ratio test, it's inconclusive if you have, the result of your ratio test being 1. Or the absolute value of your ratio test is 1. So we can look at both of the cases where x minus 5 equals, the absolute value of x minus 5 equals 1. The first case is here, where x minus 5 could equal positive 1. In that case, the series would be the harmonic series and would diverge. Here's the second case, where the absolute value of x minus 5 equals 1, but here we've set it to negative 1, and that would be the alternating harmonic series, and therefore would converge. So that's where they get this refinement from this part that we initially got from the ratio test for sure. The idea is you do the ratio test, you're able to find kind of the general interval of convergence, and then you refine that down to see, you test both of the endpoints to see whether the endpoints converge or not. Moving on. And here is just a visual of what this looks like. I forgot to pull this up on GeoGebra, but I did it on GeoGebra. Hopefully it will pull up in real time for some of the other ones. But you can see on this slide that, we're working with, this sum from part A. And for each partial sum that's here, this is the first partial sum, second partial sum, third partial sum, fourth partial sum. We are adding on a new term, and for each new term, you get a higher degree polynomial. And so, each one of these partial sums of a power series is a polynomial of degree n. And you can see that there's this dotted line here. We don't know what that is right now, but we're actually going to show you what that is by the end of this lesson. But that's a function that this power series is converging to at least over this interval from 4 to 6, like we said. So I think it was, yeah, what was it? Yeah, it was or equal to for this part and kind of open circle over here. Um, but yeah, it's only going to converge to that mystery function. Let's just call it f of x for now, um, over that certain interval of convergence. Okay, let's keep going. We will revisit that before the end of the lesson. Okay, just to remind you what part B was. There we go. Part B was this one that looked like an alternating series of some sort. That's going to come into play. Okay, here's the ratio test on that alternating series. And you can see we come to a similar result as last time. As n goes to infinity, we're just left with the absolute value of x as the result of our ratio test. And that tells us that x needs to be in between 1 and -1. And we're going to test what happens when x equals 1 or x equals -1 to figure out whether the endpoints will converge as well. All right, so there's that. Here's one of the x points when x equals 1. We would converge according to the alternating series test. And when we throw in x equals -1, yeah, the -1 that we have here, that's alternating, actually meshes up with this -1 that would be alternating. And we end up getting something that looks like the negative of the harmonic series, and that part would diverge. So again, we've got one endpoint that does converge and one endpoint that doesn't. It's not always going to necessarily happen that way. Sometimes both endpoints could converge, sometimes neither will. But those are the first two examples. Both of those had a radius of convergence of 1. Here we are centered at 0, and we can go 1 either way in either direction, positive or negative. Moving on to the last one. The last one was the one with that factorial. And here's what the ratio test looks like. The n plus 1th term up here and the nth term down here. And here you can see that if we look at what happens when n goes to infinity, that whole thing is going to go to infinity, no matter what x is, unless x is identically 0. And so this power series diverges everywhere except for when x equals 0, and then the series would have a sum of 0. So, yeah, there's really no interval of convergence here. It just only converges for one value, and it's pretty trivial that it would converge if you just add up a bunch of zeros. Okay, here we are talking about more in the power series. Yeah, the fact that if you are, cut off the tail of a power series and you're just looking at the first n terms, that's really just a polynomial. And there's a lot to be said about the fact that there are definite similarities and differences between polynomials and power series. And we're going to look at some of those properties here. We are hoping that power series will be as nice to integrate and differentiate as polynomials are. The fact that we could just do it term by term would be great. And yes, there are actual connections to be made there, and we can actually, for given power series, describe a relationship between the power series and the closed form of some function, basically, for the picture that we had earlier, this one, we are, for a given power series, we're going to be able to figure out what that f of x is. And vice versa. We should be going both ways. In this chapter, in this section, we're going mainly from the power series direction towards the function that we are converging towards. Whereas in the next section, when we talk about Taylor series, we will be converting functions into power series based on their higher order derivatives. So that's something to look forward to. There's definitely connections to be made there. That's all those are saying. Example number 2. Let's determine when these converge or diverge for whatever given value, whatever values of x. Here's probably the most plain power series that you could think of, and here's one that's pretty similar. These ones should remind you a lot of geometric series, right? So they're gonna follow that pattern. So definitely this first one converges when the absolute value of x is less than 1. And we actually have a function that gives us the value of that power series. So because we know so much about geometric series, we can actually use that not just one. For geometric series, we were using this formula where A was the first term and R was the constant ratio between successive terms. This formula translates into 1 over 1 minus x in this context because the first term is 1 and our constant ratio between successive terms will just be whatever x is. And so there's our first pair. This power series, of which these are just little partial sums, end up converging to the function 1 over 1 minus x. And I made a GeoGebra for this, so let me try to open it. I hope it doesn't give me too many problems. Come on. I'm signed in already, please. Okay, Google. For real? You can see what I'm typing. All right, I'm not going to sign into GeoGebra on my stinking tablet while the video's going. All right. I'm such a... All right. Frustrated with myself that I didn't open that ahead of time and didn't know that I wasn't signed into this version. But do trust that I have a cool interactive on here. Maybe I'll make a separate video with this. I don't know. But I have to do this in one take. But there's a cool GeoGebra thing where you can see the number of terms in the polynomial increasing and how that polynomial converges towards the given function. It's more dynamic. I think it's cool to see how it grows. Anyways, there we are. I will try to incorporate the GeoGebra thing. That is a letdown. All right. Let's keep going. Yeah, but they would converge. The partial sums there are converging towards the actual function. Okay, and here would be a very similar analysis for this one, and I have this one on GeoGebra as well. The interval of convergence here is going to be a little bit wider since we have that divided by 3 inside the parentheses. instead of just being a radius of 1 on the last problem, we were centered at 0, and we could go 1 to the left or 1 to the right. In this problem, we are centered at 1. We've got this x minus 1 piece here. So we're centered at the x value 1. 1 is our a. And then on either side of that, we're able to go 3 units. So in the center, we have 1, and we're able to go 3 units to the right or 3 units to the left. And that's our interval of convergence. And again, we could test to see what happens when x equals -2 or x equals 4. But yeah, in order to find the function that this thing is approaching, again, we can use that formula for the geometric series. This is our ratio between successive terms in this context. So it's taking the place of r. And yeah, you get this function when you simplify that. 3 over 4 minus x. And again, I had it on GeoGebra, nicely showing you how these partial sums converge. Although we have, studied only a few power series, sure. We've been able to show that they do converge for some interval. Yes, there are actually 3 cases that we're going to talk about pretty soon. Either the power series can only converge at one point, the point where it's centered, and that's pretty boring. It can have an interval of convergence that, it's bounded by some finite numbers, like most of the examples that we just looked at. And then the other one is we can have a radius of convergence that is infinite, and our power series can converge for all real numbers when the ratio test gives us that kind of a result, which we'll see soon. Okay, this power series convergence theorem, what do we say here? If a power series converges for some value x equals b, that's not equal to 0, then it converges for all x such that the absolute value of b, or absolute value of x is less than the absolute value of b. On the other hand, if we diverge, then everything greater than some divergent value would diverge as well. So, this should make sense. Do know here that we are working with this general power series that is centered at 0, and that's why we're able to make this specific claim about the absolute values of these points. But yeah, we're fine. Yes, and this is really going back to the definition of what it means for a series to converge. We've got this big N greater than N argument again. And basically we're bounding this thing above and using the direct comparison test using a geometric series. This x minus b here would be less than 1 when the absolute value of x is less than the absolute value of b. We're using the direct comparison test. We've got this convergent geometric series that bounds this thing, and this is just the divergent case where, we'd show that things that are bigger than a divergent series also diverge. Not terribly important to understand all the intricacies of that. Cool, and that definitely applies to things more in general where we're centered at some other value other than 0. We're fine. Okay, I've been using these terms somewhat cavalierly so far. Radius of convergence and then interval of convergence are the new vocabulary words on this slide. Um, yeah, and we've got these different possibilities. Here's where it's talking about the radius that is 0. That is, we only converge at one point when x equals a. Um, that's, kind of case number 1. This part, if we've got a radius that's infinite, that's kind of case number 2, and the series would converge for all x. And then we've got this third case down here where we're bounded by some finite numbers. And yeah, depending on whether the endpoints converge or not, you could get any of those 4 possibilities for interval notation. So yeah, this is, cases 1, 2, and 3 here. Converge only at one point for all real values or for some interval of the real numbers. Example number 3. Here we've got part A, where we've got some geometric stuff going on top. We got a factorial on bottom. And then more geometric stuff on top on part B, and some square root stuff on bottom here. So let's take a look. Again, we're going to use the ratio tests to determine radius of convergence. In this case, we get 1 over n plus 1, which goes to 0 as n goes to infinity. And therefore, the radius of convergence here is everywhere. It doesn't matter what value of x we put in. This product is still going to go to 0 as n goes to infinity. And again, on GeoGebra, I had that first one done out. What this one looks like is you got x to the, well, this is kind of weird. X to the 0 over 0 factorial plus x to the first over 1 factorial, x squared over 2 factorial, so on and so forth. This one actually ends up converging to e to the x. It's a very special function in calculus, right? The only function that is its own derivative. And so, yeah, it's actually a really cool series, and it's very nice that this thing converges everywhere. At every real number, this power series converges towards the function e to the x. And you could see that if I had GeoGebra ready. Sorry. I'm not angry. For part B here, we've got that geometric part with the negative 2x thing, and then we've got the square root part. Again, as n goes on, this thing's going to get, closer and closer to 1. And so this thing approaches 2 times the absolute value of x. And then the radius of convergence is 1/2. And again, we would need to test those endpoints separately to determine, exactly what the interval of convergence would be. When x is 1/2, we have an alternating series, and when x is negative 1/2, it's this divergent p series where p is 1/2. So the interval convergence is here. This means the same exact thing as x being greater than negative 1/2 and simultaneously less than or equal to 1/2. Cool. We're not at the end. Keep going. All right. Here's where we get to start doing some calculus on the power series. Yeah. we really can just go term by term. And we're using the power rule basically a zillion times along the way here, an infinite number of times. But yeah, this is how you take the derivative of that starting power series, just the power rule. And here's how you take the antiderivative. You add 1 to the power and divide by that power. Like we're used to working with polynomials when we integrate or differentiate. Yeah, and these series have the same radius of convergence as the series that started off with. So yeah, f prime has the same radius of convergence as f, but it could be possible that the endpoints change a little bit. So if you ever wanted to really determine the complete interval of convergence, you'd have to test the endpoints again for a derivative or antiderivative that you found. I guess one thing, to notice, since we're taking the derivative here, there our index starts at 0. Here our index starts at 1, since when you take a derivative, you lose the constant term. And so that's, what happens there. So the C0 gets lost. This one, the interval, or the index starts at 0 again here, but we actually add another term on, and that's the plus c that you normally get when you take an antiderivative. Okay. Yes, power series behave very well when integrated and differentiated. You just go term by term. Not all series are so well behaved. I believe that you will, especially the people who are going into engineering, you're going to encounter more varied series, Fourier series, that kind of stuff as you go on. And yeah, not everything is as well behaved as a power series. Here we go. We've already looked at what this power series is. Remember that we said that is equivalent to the function 1 over 1 minus x, because this is, basically a geometric series where that constant ratio is x. And so we're going to take the derivative both in the power series form and in the closed form and, look at what happens. So taking the derivative in the power series looks like that. We subtract 1 from the power, we bring the power down and then subtract 1 from the power and get this version. And then taking the derivative of the closed form, you get this closed form. Again, using the power rule. And, maybe a little bit of the chain rule there. You just have to bring a negative sign along. But yeah, we actually, just by, taking the derivative of this power series, we create a new power series. And since we had the closed form of the previous one, we have the closed form now of the new power series. And that's pretty cool. The radius of convergence, again, is 1. And the interval convergence is, here. Neither of the endpoints converge in this case. So that's cool. So that was differentiating a power series. Here we are going to look at what happens integrating a power series. Even before we get started, it will be helpful to notice that start off with this one and you take its antiderivative by adding 1 to the power and then dividing by the power, you get this one. notice here that the index has changed, and that gives us, the fact that we've got one more term. But yeah, so that the second series is the one that is easier to analyze. And so that's what we're doing. We've got this geometric series. And again, we can figure that out using our formula for finding the sum of a geometric series. And we get this function, 1 over 6 minus x. If we notice that, we take an antiderivative here, and term by term, find that, we get an antiderivative. We can do the same thing here. We take the antiderivative of this, and if we take the antiderivative of this one, we will find the closed form of this first one. Well, we'll find the closed form. That's what's going to happen here. The radius of convergence here is 1 again. Okay. And so what we do is, we can take the antiderivative of the closed form here, and we get a closed form for the first series. And we could figure out what that plus c is by substituting in x equals 5. If you substitute x equals 5, that would make this entire top part 0 here. And so we know that sum should be 0. And, therefore, this part should work out to be 0 as well. And indeed, if you do 6 minus 5, you get the ln of 1, which is 0. And that means that we don't need, a different plus c out here at the end other than just c equals 0. Cool. And this is the very last thing. Power series can behave like polynomials in that you can multiply term by term, basically using the distributive property on steroids. I mean, think about this as like, FOIL on steroids. You're finding all of the, coefficients here for a given power. So what we have is two convergent power series, f of x and g of x. And we're looking at the product of those two things. We can figure out what the coefficients need to be here on, our nth term by looking at all of these products. Basically we've got n products here that add up to Cn. And I don't know, you guys I know are just maybe starting with some of the vector stuff out there, but looking at this reminds me of a dot product. Definitely reminds me of a dot product. So if that's helpful, cool. If not, no big deal. But you can find all of the coefficients there. And this result is actually really important for proving the convergence or divergence of really famous series. I don't know if you got a chance to look at it yet, but remember the series where the terms had 1 over all of the different perfect squares? I put a couple videos, for instance, from 3 Blue 1 Brown or from Mathologer on our YouTube playlist. And if you haven't taken a look at those yet, now would be a good time to go ahead and look at those. Because again, those actually are very relevant to, Power Series. Especially the Mathologer video makes use of the fact that you can multiply things within a Power Series. And then you're able to, equate these coefficients between two different ways of looking at a Power Series. And you're able to come up with really, really powerful, results like, hey, I know that series of 1 over all of the perfect squares, that series converges to pi squared over 6. That's crazy, but it happens because, we're using this property that you can multiply Power Series stuff together. So I believe that is all for today. This has been How to Math. Please remember to stay up to date on your online homework. I just this morning worked through your final. I am in the process of, writing up an announcement for you guys so that you know exactly what's going to happen. But basically, it's 25 problems on Hawks. I'm going to give you basically the entire last week of classes to work on it. And you'll be able to take it, as many times as you need to in order to, get the grade that you want. So, more details will follow on that. But I am, finalizing the structure of your grade, the final exam and what that'll count as. So there is some light at the end of the tunnel here. I miss you guys. I miss seeing you. I will hopefully see all of you next semester in Calc 3. But that's all for today. I would be happy to chat on Pronto if you have any questions. All right. See you in the next one.